Length of last word. Given a string consisting of words and spaces, return the length of the last word in the string. A word is a maximal substring consisting of non-spaced characters only. You know what a word is. Okay, so for this kind of problem, it's pretty easy. So if you get asked this in an interview, you should be busting through it as quickly as possible. I'm going to take a little bit longer than I would expect you to take in the real setting, and I'm going to go through things a little more thoroughly and explain each piece as I go. So this particular algorithm, okay, let's start illustrating this by an example. You have this first input here, hello world. They want to tell you the length of the last word in the string. So in this case, world. What is the length of world? But all you're given is this string, so how do you find it? Well, the naive approach is you find the last word and then you count its characters. Actually, the brute force approach isn't really any different from the optimal approach. There's only really one way to do this. All right, so this example here, input number 2 is probably the more tricky one, and this is the one I'm going to do when I step through like the runtime example. Fly me to the moon. You have to find moon and then count its length. But notice there's a couple of extra spaces here, so that's an extra scenario. That's an extra type of case we're going to have to check for in our runtime. So when you do these kinds of problems, the steps you should follow are, first, you want to think about runtimes in an algorithmic big O asymptotic sense. Now, I'm not going to go and explain how that works or how to do asymptotic analysis. I'm just going to perform it as we go. And I'll put a link in the description below. There are many, many excellent resources throughout the internet that explain big O notation and asymptotic analysis. And we'll just use those concepts here. So what you should do is choose a asymptotic runtime before you start coding. You talk about different approaches, and you pick a target runtime that you're going to build your algorithm around. And then as you go, you're going to consider how your code does or does not affect this runtime, and if you'll be able to achieve the target or not. The idea is you want to code with intention. The intention being to match or do better than, probably not do better than, but at least match your target runtime. And the other thing you're going to do is you're going to take an example input. Either you can come up with one, or maybe the interviewer will give you one. It kind of depends, but be prepared to come up with one if needed. And you're going to mentally step through it without executing any code, but you're going to run this code in your head as if you are the computer. And the reasoning for that is because when you work on really, really big projects, sometimes things like tab completion don't work, because those are creatures of the development environment program that you'll be using, and sometimes they just can't grasp these, make multi-gigabyte, millions of lines of code projects. You'll only be looking at a small piece of it, and an IDE is not going to be able to do it justice. So effectively, you'll be working out of a raw text editor. And that's not ideal, but it happens all the time. And so this is something they check for in interviews. And the last thing you'll want to consider is edge cases, in addition to your normal type of input. So for example, if you get some weird adversarial input that matches your given constraints but is still weird. So for example, here they said the length of the string is at least 1. Okay, what happens when your string is just 1 character? Will your algorithm still work? What happens when your string is 10 to the 4th long? What happens when your string is all spaces? What happens when your string is all one big, very long word? All those kinds of things are stuff you should consider, and especially consider them if your approach that you're going for doesn't necessarily handle them through the main line of processing. So maybe you have to put an if case at the start of your solution. So let's talk about this problem at hand. It's a string, and you need to find the last word. There's no sorted element to this. There's no alphabetical ordering or any kind of way you can look at one part of the word and know if your last word is to the left or right of it. there's no really way to do that. And the reason that's important is because if it were possible, you could start looking at an O of log n runtime, so logarithmic. And that's only possible if you have a way to avoid touching upon parts of the input. That's not really the case here. It looks like we're going to have to touch on each character at least once, if for nothing else, to look for spaces and define where that last word begins and ends. And like I said, with the edge cases, suppose your entire string is one very, very long word. Well, asymptotic analysis is about the worst case scenario. You're finding your worst case runtime, and our worst case is suppose the entire string is one word. Well, now you have to find the length of that word. Okay? So if that were the case, you could just say take the length of the entire string, and that would be something you could do in constant time. Generally, strings maintain, in C++ and in most languages, a string maintains a property where you can find its length, or at the very least, you already have pointers to the start and end of it, and you can just like do a difference between them. At least in C++ that's the case. Maybe that's not always the case in C, where strings are sometimes implemented as just a pointer, and you have no idea what the length is, in which case you still have to scan it in linear time. In this case, it's a C++ string. We know its size in constant time. But how do you distinguish when the entire string is one word, or if there's a space somewhere in the middle? There's no way around touching on every single character at least once, potentially, to know that there isn't a space somewhere in there. So we're looking at linear time, O of n time. O of n, so n being the size of the input. So our runtime is linearly proportional to the size of the input. That's going to be our target runtime, is O of n. And if we do worse than that, we know we're doing something wrong. If we do better than that, we're probably doing something wrong, probably missing something somewhere, and there'll be some correctness issue. So we're really looking for O of n. And let me go ahead and write that down so that the interviewer remembers what we're doing. And as a general rule of thumb, I don't see this recommended in most places, but I think it would be a very good idea to write down your thoughts as you go so that there's no question. Sometimes interviewers, they're people too. They're thinking about their other priorities. They got distractions around them. Stuff's going on. They're not always as professional as they should be, even for big multi-billion-dollar corporations. And these people are being paid, six-figure salaries, multi-six-figure salaries. They're still people, and stuff goes wrong. And if you don't account for it, you're the one who suffers. So go ahead and write your stuff down. So our target runtime is we're looking at O of n. And what about space complexity? General rule, space complexity is usually less varied than time complexity. It's a similar concept, but the differences are usually kind of the same. Usually it comes down to, most of the time, you're looking at either constant space if you don't have to copy the input, or linear space if you do have to copy the input. In this case, what I'm going to do is I'm going to scan back to front, because it's a C++ string, so we know the size of the string. We have a way to access the end of it in constant time. So I'm going to start at the back. I'm going to count, skipping spaces until I find a non-space. And then I'm going to count the non-spaces until I hit another space or the beginning of the string. And then that will be my size. So that is this many steps. And that's just a linear, search. One, boom, 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 boom. That's going to be my algorithm. So what data do I need in order to perform that? I need 2 pointers. I need, really just one, actually. I need an integer to include the size, my running total, and a pointer to access where I'm currently at. So like an index value or an iterator or something to access the value in the string. And then at the end of it, I'm going to return that integer that I've been counting up. So let's go ahead and add those. Int, and I'm just going to call it ret for return. Usually the return value, you could name it a lot of things. I found I have a personal preference for naming it something consistent, something maybe more meaningful about what you do with it as opposed to what it contains. Particularly for these algorithm problems, I just call it ret for return. You could call it res for result, whatever you prefer. And we start out with our possibility that the size of the last word is 0. And this would happen if the whole string is just a bunch of spaces. And that's fine, that accounts for it. So, okay, so we've got a return value. And then what I'm going to do is I'm going to do 2 for loops, and I'll explain it as I go. So, first, let's do for string iterator. Let's see if I hope I remember the syntax. String iterator it equals s.rend. And this isn't rend the word as in like render. This is reverse end. So what this method does is this is a property that pretty much any iterable container has, which is basically all containers. In this case, a string is basically a more specific case of a vector of characters or an array of characters. So reverse end. And what this does is we can act this basically a pointer. C iterators are unique to C++ more or less, but they're basically pointers. And we'll show how to use those there. So this gives us an iterator pointing to the reverse end. So wait, actually, no. I was getting that wrong. So R begin. Okay, reverse end will be important. R begin, reverse begin. So if we were to iterate through backwards, what is the first iterator that we want to go in reverse? That's the very end of the string, so reverse begin. And then while, so our exit condition is going to be iterator does not equal s.rend. Okay, that's the case where that is. Rend and the contents of it equals space. Okay, what this means is this gives us an iterator to the first character if we were stepping backwards, so the end of the string. Reverse end is an iterator that points past the last position again in this reverse order. So one before the first character in the string. So it points there, which is invalid. So if we try and access it, we're going to hit an error. But that's the way C++ iterators work, is generally end, so dot end, or which is the normal iterator if you're going from left to right, or rend for reverse end if you're going right to left. Those will point one past the last valid position. So that's what those mean. And then, so we're checking this first so that if we hit the beginning of the string, we don't try to access an invalid position. But, and then we just won't run this if we're hitting that. And what this star does, it's, same syntax as with pointers. It's the value inside. So this iterator is more or less a memory address reference. So the value inside that address, we're checking it and we're comparing it to the space character. And we're using single quotes for character because double quotes refers to a string, which in C at least, even a one character strings, C style strings always have one extra null byte at the end. So they're one character longer than the display. If you do single quotes, that tells the compiler, okay, this is definitely just a character. It's not a string. Don't tack on an extra null byte at the end. What you see is what you get. That's what that means. And then in between, so after each iteration of the loop, we're going to go ahead and increment. And then that's pretty self-explanatory. Notice that we're going right to left, but it's the library handles that for us, so we still increment it. It's a reverse iterator, but incrementing it, even though we're boosting it up by 1, it's still going to go right to left when we do that. Okay, so we have our first loop, and then so we're checking for spaces in this case. Actually, I'm going to take that out of there. Put it there. And the reason for that is because we don't want to do it after. I can't recall off the top of my head. This is something I should know, and I should check documentation on. If this command executes after the last iteration of the loop, but I definitely do not want it to execute after the last iteration of this loop, because we want this this iterator, to point to the last character of the last word. And actually what I'm going to do here, because we want to keep this, I want to keep that, is I'm going to bring the declaration outside the loop because I want to use it in the next loop as well. So that, you'll notice that this for loop's looking pretty wonky now. So a for loop is basically an abstraction of a while loop in C++. This first statement is what happens at the beginning of the whole loop. So you can declare variables, you can do anything that's valid, and it happens once before the beginning of the loop. There's an exit condition here in the middle, and this is checked. This should return a Boolean, and it's checked before each and every iteration of the loop. And as long as it's true, you'll keep going. And if it comes out false, that's when you exit the loop and you break out. And this last statement happens each time after the loop. So normally people would increment their index counter there, whatever. But and all of these are optional. You don't have to do them. But typically, so if you have like a null statement that might return false, I'm not actually totally sure on that. But we have this here, and this effectively turns our for loop into a while loop. I could just say while loop. I don't know. This is fine too. Maybe something to talk about your interviewer with. You know what? The compiler's not going to know. I got to think about this. There may be some slight differences on how the compiler brings in optimizations on for loops versus while loops. Generally, for loops are easier to optimize under the hood from the compiler's perspective. Now, that said, any compiler worth its salt should still be able to tell this should be able to tell this is basically a while loop or a while loop. It should wash out if you have optimization flags turned on. But if you don't, that's when it might start to matter. I don't know. It's worth mentioning with your interviewer. And if they don't like it, then you could just change it to this. And maybe this is more readable for normal people for programmers. I'll just leave it like this because this is more normal. Even if in runtime it may not necessarily matter. Okay, so we've skipped past now all of the spaces within, at the tail end of the string. Now, what I want to do is count the size of this last word. So we skipped here. Now we're pointing here at n. We want to go here until we hit a space and then find the difference. All right, so while it does not equal, same condition, s.rend and iterator does not equal a space character. This is pretty similar to the above scenario. So first we're making sure that our iterator is inbound, so it's reverse end is before the start of the string. So if you try to access it, you're going to get an error. So as long as we're not there and we're still at a valid character, we look inside it and then we compare it to a space. And if it's not a space, then we know it's part of that word. So we do two things. Going to increment our return value because we know it's a valid character in the string. And we increment this iterator, same as before. Yeah, so as long as it's valid, not a space, that, and then this. And then once this condition breaks, we know we're past the beginning. We're to the left of the beginning of our final word. And then we don't care what happens before that. At that point, we're going to break out and return. So that's what we'll do. So go ahead and return ret, and that's our algorithm. So we've got it written out. We've got our target runtime and O of 1 space because we just had integers. Let's go ahead. I'm going to go ahead and step through first each line and then analyze the time and space to make sure it matches our target, what we plan to head versus what it is as implemented, and then we'll do an example. So this is initializing constant. A little bit of a background. So operations are really linear time on the number of bits. But when you deal with real machines, typically the number of bits in a variable are a fixed size. At least within that machine, they're a fixed size. So it could be 32 bits, could be 64 bits, maybe in the future it'll be 128, 256 bits, whatever. But for that machine, it's a constant number of bits, meaning operations on it are constant time. So initializing this return value is constant time. And same thing with getting our iterator. This is a known thing that the standard library container maintains, and it can get it to you in constant time. So that's constant. And then this while loop, we're doing a constant time operation within it to increment the reverse iterator. And we're doing 2 constant time comparisons. So that's 3 constant time things. But suppose the whole word is all spaces. Well, this is linear time because we're doing a linear number of steps, constant time per step. Same thing with this second loop. It's again going through, up till the beginning of the word. It's doing a constant time comparison here, a constant time accessing comparison here, and 2 constant time variable changes here. So that's 4 constant time operations. For suppose the whole input is one very long word, well then this is a linear time loop, linear number of steps. But also notice that we're using the same iterator for both of these. So what that means is no matter what worst case scenario, you're still going through the whole loop, the whole string, only the once between the two. So it's really like 2 halves of one linear time loop. That's what that is. But regardless, the way that linear time works, or asymptotic time works in general, is if you do something more than once but a constant number of times, well, that doesn't change the asymptotic properties. So 2 O of n loops, if you are still O of n time, as long as there's only 2 of them. But in this case, it's really just the one, so 2 halves of the same one, and then a constant time return value. And then as far as space goes, well, we allocate an integer here, we allocate an iterator there, and I think that's it. It's just those 2 things. So that's our constant space complexity as well. That's it. It doesn't change on the size of the input. Let's go ahead and do the example. We've got this bad boy. So fly me to the moon, and then we've got start off our return value. And then we have, I'm going to use a star for the iterator. So let's do, to the left of the star is where the iterator is currently pointing. So start off at 0. Start off the iterator is reverse begin, so pointing to the last character in the string. All right, so while the iterator is not past the beginning, so it's not equal to reverse end. So while it's not there, that's not true, so that's fine. That means we're going to check this too. The contents of it are equal to a space. So we're going to go ahead and increment the reverse iterator, meaning we move it 1 to the left. And then we check that again. We are not past the beginning of the string, and the contents of it are still another space. So we're going to go ahead and increment it again, which means moving it 1 to the left. Things are a little different here. So while we are not past the beginning of the string, but the contents of our iterator are they are not equal to a space. So we're not going to enter this part of the loop. We're going to exit out of this loop and keep going here. So then we check this condition here while the iterator is not past the end. Okay, well, we just checked that before, but it's still the case now that we are not over here. And now we check it, and it is not equal to a space, meaning we're going to enter this part of the loop and do these 2 operations here. So we're going to increment our return value, and we're going to move the iterator. We're going to bump it by 1, which means moving 1 to the left. So there. And then we do it again. So check, we are not here at the beginning. The contents are not a space. So then we increment this, and we increment the iterator, which means putting it 1 to the left. And then we're going to do that 2 more times. So we're not there. The contents are not a space. So it means we increment the output, and we move the iterator 1 to the left. And then last time, do the same thing. We are not there, and the contents are not a space. So to the left of the star here in my syntax here, it's an M, not a space. So then we're going to bump up the input, and we're going to move the iterator 1 to the left. Now we're going to check this condition again. We are not 1 to the left, but the contents of it, of what our iterator is pointing to, it is a space here. So that means this condition is no longer true, meaning this overall Boolean condition with the and relationship is no longer true. So we're not going to enter the contents of it. We're going to break out of the loop. And the only thing left to do is return our output value 4. And that is our expected return value. And we thought, okay, would this work with edge cases? Do I need to add anything about edge cases? Suppose the string is empty. Well, I take care of that here, initializing it to 0. Actually, well, our string is going to be at least 1 character long. So initialize return value to 0, yes. And our iterator is going to point to the one lone character in it. And then we'll hit this. Okay, suppose it's a single letter, like the letter A. Suppose we have this. Okay, we are not past the beginning, and then our contents are not a space, so we're not going to enter here. So then we hit this loop, same thing, we're not past the beginning. The contents are not a space, so we're going to increment return value by 1, increment the pointer. And in this case, we're going to see we are, so we're pointing to the left, meaning we are now 1 past the beginning of the string. So this condition is going to be false. We are now equal to reverse end. And then we're going to break out and return. So that's fine with there. And then if it's a space, suppose that we have a space here. So initialize to 0. Our pointer is now pointing there. Let's see, what do we do? So this is going to be true. We are not pointing past the end. And then this iterator contents are a space, so we're going to bump it over to the left there with this. And then we're going to check here. So now we are equal to s.rend. So the reverse end, we're pointing 1 before the beginning of the string. This is no longer true, so we don't do this. Oops. And then same here. So we see that same condition is going to make us not enter this loop at all either. And then we're going to return 0. The length of our string is 0. Okay, I think that works for that. And then our logic should be okay for super long strings here either. There's not really, I can't think of any kind of like case where that would be a complication from this algorithm either. Those are our 2 edge cases. So I don't need to add any like special handling at the beginning of this function for edge cases. I think that's it. I'm going to go ahead and give it a run for syntax, and hopefully that works. What did I do? String, iterator, you know, I can't remember I don't remember how to declare iterators for strings. I'm pretty sure it's this. So okay, normally if you have, say your input is a vector, so you've got some vector. So if you want to declare an iterator, you could say like vector, whatever. If it's a vector of integers, you say vector, and then you colon iterator. You could do that. That's normally how you do it. I think so if it was an array of characters, you could say like vector of characters, and it would do that too. I don't actually know. It's better form to declare your data types explicitly in an interview in particular, because, okay, there's an alternative you can use in modern C++ called auto, where it just figures out what data type you need based on what you assign it. So you can't, for example, do like auto x and then that's it. That's not valid because you need to assign it to give it a data type. But what you can do is like auto x equals, whatever. And 0 it defaults to an integer. So it'll make x an integer. And then from there on out, x can only be used as an integer. So if I use auto here, whatever this r_begin data type is, it will assign it to it because of this auto keyword. And this is just something I thought it was string iterator. Apparently it's not. This is something that works perfectly fine It's perfectly valid C++. The compiler will know exactly what you mean. The only difference is it doesn't make it as obvious what the data type is unless you know what this is. But also I'm naming it like it, so if your word, maybe you could do like sit for string iterator, or you could give it a more verbose name. Generally with interviews in particular, I would recommend using shorter variable names than you would use in normal production code. So normally in regular code, you would treat the variables basically as comments. So you'd name them sometimes very verbosely, depending on the coding style of the project that you're on, but sometimes the variable names can be quite long. In an interview, since you're typing it out and you don't have access to things like tab completion, and then copy paste is also, it's allowed, but it's risky. Copy paste is always risky. So I would recommend using short variable names, and then maybe what you can do is write out like a key in wherever, saying like so it. So if you name it like it, it'd be like string iterator. Or like writing out something about what it is, or if you were to name it like, because sit is a weird variable. Sit is less common. You write out some key, just like talk about what it is, and then you use the short variable name from there on out. So you have less characters to type each and every time you use it. That's also an option. So this should work with auto now. That should be fine. So let's go ahead and give that another run for syntax. No, what I miss? Use of undefined. Oh, yeah. Let's keep the name inconsistent. It is it throughout, so let's keep it that way. Okay, that's better. So that's accepted. I'm going to go ahead and submit. Boom. Beautiful. So don't get too hung up on like rankings that LeetCode might show you. They give you like an absolute runtime, or it beats, whatever percent of users. Generally, that's not important except for very niche roles, which that is, okay. High performance computing is the case where you generally start getting into multi-threaded programming and things where like every blessed millisecond starts to matter. When you're dealing with big data applications, and for most big companies, they're not expecting you to do these kinds of micro optimizations that save time in the real world. They're expecting you mostly to talk about asymptotic runtime. So O of n versus O of log n versus O of n squared, which would be O of n squared would be if your runtime increases by another factor of n for each additional like increase by 1 in your input. So the runtime is the square of the size of the input, or in this case here it's linear. They're proportionally linear to the size of the input. Don't worry about rankings. They're really not important. And same thing for memory. What you want is to worry about the asymptotic analysis and make sure you have that down pat. Before you start coding, you have a target value that you're coding to, and then compare what you achieve and implement versus what you targeted. And don't worry about this unless you're going for a specifically high performance compute role, where maybe they'll start asking you about stuff like that. And even in those cases, they might just want to make sure you know how to measure it. So in which case, do you know library functions for taking time measurements and taking the difference between them and comparing that way and that sort of thing. Anyway, this is wrapped up. And that's all there is to say about it. Length of last word. Thanks. You have a beautiful evening.